You'll recall how we used the inverse square law when we covered star luminosity in the nearby star segment. We measured the brightness and calculated the distance from parallax measurements to get the luminosity. But if we had a way to know what the intrinsic luminosity of a star was, we could use that, along with the apparent brightness, to get the distance. For example, if we measured the brightness of a 10-watt candle from some distance away to be 1/10 of a watt per square meter, we could calculate that the candle is just under 3 meters away. A celestial object with a known luminosity is called a standard candle. But until 1912, there were no known standard candle stars. That changed when Henrietta Leavitt published her findings on Cepheid variable stars.
For most of its life, a star is quite stable, slowly consuming the hydrogen at its core to keep it shining brightly. But when most of the hydrogen has been consumed, some stars evolve into very different beasts known as variable stars. They become unstable and start pulsating, expanding and shrinking over a number of days or weeks and growing brighter and dimmer as they do so. RS Puppis is one such variable star, a type known as a Cepheid variable. It varies in brightness by almost a factor of 5 every 40 days or so, and is engulfed in a thick shroud of cosmic gas and dust. Hubble gazed at RS Puppis over a period of around 5 weeks back in 2010, observing it growing brighter and dimmer within its murky surroundings. This enabled scientists to create a time-lapse video that appears to show the gas around the star expanding outwards. However, this gas is not actually moving. It is an optical illusion known as a light echo. The dusty environment around RS Puppis allows us to see this light echo with stunning clarity. As the star expands and brightens, some of the light does not reach Hubble directly, but is first reflected off progressively more distant shells of dust and gas surrounding the star. This reflected light has further to travel, and so arrives at the Earth later than the light that has travelled straight from star to telescope. Hubble also observed a light echo around variable star V838 Monocerotis in 2002. This is very much like the experience of an audible echo, where the listener hears a sound once and then again as the second wave takes a longer path, bouncing off surrounding objects. Beyond the striking beauty of this effect, there is an important scientific reason to observe Cepheids like RS Puppis. The period of their pulsations is known to be directly connected to their intrinsic brightness, which allows astronomers to use them as cosmic distance markers. Astronomers have measured the distance to RS Puppis, calculating it to be around 6,500 light-years, the most accurate distance to such a star ever measured.
All stars grow and change throughout their lives. Some stars explode at the end of their lives, and we call those explosions supernovae. This happens to stars that are very large, much larger than our Sun. Our Sun, which is a medium-mass star, will instead eventually discard its outer layers, exposing just the core. This core is small, hot, and bright, and roughly the size of the Earth. We call it a white dwarf. White dwarfs don't explode unless they eat too much and gain too much mass. An explosion like this is called a Type 1a supernova. When white dwarfs explode, they always give off about the same amount of light, and this means that we can use them to measure distances in the universe. Just as distant streetlights look dimmer than ones closer to us, distant Type 1a supernovae look dimmer than nearby supernovae. This is how we can work out distances. When astronomers used this technique, they found some very interesting information about the universe. They discovered that the expansion of the universe hasn't been slowing down since the Big Bang, but speeding up. However, we still don't know what kind of energy is causing this, so we call it dark energy. This dark energy makes up about 72% of the universe. Although we know that white dwarfs grow and explode, we're not sure exactly what makes them grow in the first place. Most stars in the universe have at least one companion star. Could two white dwarfs merge together? Or could a white dwarf steal mass from another star? If a white dwarf steals mass from a star like the Sun, then the explosion, the supernova, will hit the Sun and glow blue. We've seen this, but it doesn't happen all the time. Right now, astronomers are trying to figure out if there are many different ways a white dwarf explosion can happen, or if there is only one. Using Las Cumbres Observatory, we can monitor these events within minutes of them being discovered, right from the crucial first hours, then over the days or months as the brightness changes. Las Cumbres Observatory's unique robotic telescope network has the potential to revolutionize what we know about these exciting cosmic explosions.
Elliptical galaxies are a type of galaxies characterized by their smooth, spherical, or ellipsoidal shape, lacking the distinct spiral arms found in spiral galaxies. It has a dense, spherical region containing a high concentration of older stars called the central badge, exhibits a range of shapes from nearly spherical E0 to more elongated ellipsoids E7 and unknown spiral galaxies. Elliptical galaxies lack a distinct disk and spiral structure. There are also different types of elliptical galaxies, like regular ellipticals that displays a smooth, featureless appearance with a relatively uniform distribution of stars, and dwarf ellipticals that are smaller in size and less luminous compared to regular ellipticals. They are often formed through the merger of smaller galaxies, leading to a more spherical shape and reduced star formation activity, and are predominantly composed of older red stars with little ongoing star formation. They are generally observed in the optical and X-ray wavelengths due to their older stellar populations and lack of significant star formation, with notable examples including M87, an enormous elliptical galaxy in the Virgo cluster. Elliptical galaxies are a major category in the Hubble sequence of galaxy classification and plays a crucial role in theories of galaxy evolution, particularly in the context of galaxy mergers and interactions. In summary, elliptical galaxies are characterized by their smooth, spherical, or ellipsoidal shape with a dense central badge, lacking spiral arms, and are often formed through mergers of smaller galaxies, featuring predominantly older stellar populations.